So far, we've explored a few ways of analyzing data, including computing and interpreting descriptive statistics and constructing a few basic plots. Now, we take a step back to discuss how to get good data in the first place. A first step is to clearly define the population you want to study. For example, let's say that you're interested in conducting a survey about smartphone usage among college students at a given university. The population here would be all college students at that university. Now, it's impractical to ask every student at the university about their smartphone usage. Instead, we take a sample of students and use what we observe in the sample to make inferences about the population on the whole. Let's think about some different ways in which we might select a sample. We could randomly select a few classes and go and survey all of the students in those classes. This type of sample is known as a cluster sample. A cluster sample involves dividing the population into clusters and randomly selecting clusters to include in the sample. Suppose that we decide that, to reflect the proportions of class levels at the university, we want to include 20 freshmen, 15 sophomores, 25 juniors, and 30 seniors in our sample. We go on to randomly select the desired number of individuals from each of these groups. Here we have a stratified sample. A stratified sample involves dividing the population into distinct subgroups, or strata, and then randomly selecting samples from each subgroup. We could conduct a survey by approaching students in the university library and asking them to participate. This type of sample is known as a convenience sample. A convenience sample involves selecting individuals who are readily available and accessible. We could create an online survey and share it on various social media platforms. The self-selected students who respond comprise the sample. Here we have a voluntary response sample. A voluntary response sample is one where individuals self-select into the sample by volunteering to participate. Cluster and stratified sampling attempt to capture the diversity in the population, but their quality rely heavily on how well the subgroups are constructed. If they aren't constructed well, potential bias can be present in the sampling. Convenience and voluntary response sampling are generally quick and inexpensive, but they often do not provide a sample that represents the population well. Any time that we represent a larger group, like a population, with a smaller one, like a sample, there is a potential for what is called selection bias. Selection bias occurs when the sample obtained is not representative of the population, and there are many ways in which this can happen. Voluntary response samples often only include those with strong opinions, while those who are more indifferent tend not to participate. Selection bias may occur when there is a large number of non-responders. For example, younger people might be less likely to respond to a survey conducted by landline phones than older people. This would lead to an overrepresentation of the views of older people. Suppose that in a study about health issues, a sample is obtained by surveying people who are currently employed. The sample may be biased because people who are working are typically healthier than those who aren't able to work. Selection bias is real and sometimes hard to account for. Before we move on, I'd like to give you a simple but potent historical example of how selection bias could have had serious consequences. In World War II, the British were losing a lot of bomber planes as they flew over Germany. In response, they decided to add armor to their planes. The armor was expensive, so to try to strengthen as many planes as possible, they decided only to armor the areas of the plane that were most critical. They collected detailed records of where the planes were shot when they returned from their bombing runs. The data strongly indicated that the returning planes had holes in the nose, the tail, and the wings. So the British decided that they would add more armor to these locations. Before making the modifications, they proposed the idea to the Statistical Research Group at Columbia University. The group looked at the data and concluded that this is the exact opposite of what should be done. Their reasoning was that the planes used to generate the data were the ones that returned from the bombing runs. Those that did not return were shot down and were likely hit in the other areas of the plane. The British added armor to those areas instead, and it resulted in remarkably fewer downed planes. Here, the selection bias presented itself by having a sample that only consisted of planes that returned. So, what's the best way to try to eliminate bias and draw a good sample that is representative of the population? The most basic, and in most cases the best, sampling method is the method of simple random sampling. A simple random sample of size n is a sample chosen by a method in which any collection of n individuals is equally likely to make up the sample. Another way of thinking about simple random sampling is that it's like a lottery. In the context of drawing a sample of students for the smartphone study, we could number the students from 1 to however many there are. Then, we could use a random number generator to get a simple random sample. In R, there is a built-in procedure for constructing simple random samples. I'm going to start by importing a dataset of 10,000 names. I'll call this student population. This dataset contains one variable called name. The sample command in R will produce a simple random sample of a specified size. Suppose we want a simple random sample of 50 student names. We use the sample command with the variable name from the student population dataset, followed by the desired sample size, which in this case is 50. Running the command, we get our simple random sample. Let's play around with the sample command a bit more. Suppose we wanted to simulate the rolling of a 6-sided die. First, I'll create a data array with the numbers 1, 2, 3, 4, 5, and 6. I'm going to call this die 1. Now there's a shortcut that I could have used here. To create a list of sequential numbers like 1 through 6, I can use the shortcut 1:6. Let's create another data array to simulate a second die, which I'll call die 2. If we call up die 1 and die 2, we see that both just contain the values from 1 to 6. Now, suppose that we roll die 1 3 times. Think about what we might get. Any combination of 3 values 1 through 6. We can simulate this using the sample command with a size of 3. If we run this a few times, we might notice that something's not quite right. Rolling a die 3 times could very well produce repeated values, like 115 or 424. However, the sample command in R doesn't seem to be producing repeated values. What's going on is that R is assuming that once it pulls a value from the population, it shouldn't be replaced. However, we can tell R to replace the population values by including the replace equals true option. Now let's run the command a few times. We see that we now have an accurate simulation of the rolling of a die. How about we take this a bit further? Let's simulate the sum when we roll 2 dice. I'm going to start by defining n, which is the number of times that I will roll the 2 dice. We can always change this value, but let's start with something like 100. So we'll be rolling 2 dice and taking the sum of the dots that appear 100 times. Okay, I'm going to roll the first die using the sample command, and don't forget the replace equals true option here. Now we'll add this to the second die using a similar command. Let's call this new data array die sum. Let's take a look at die sum. We've got 100 simulated sums that result from the random rolling of 2 dice. Well, if we can do this 100 times, why not do it more, say 1,000 times? Maybe we want to take a look at the histogram of it. I can do this using the hist command. And as we might expect, the most frequent sum that we get when rolling 2 dice is 7. So in this lesson, we discussed some different ways of selecting samples, possible sources of bias, and some basics about using R to generate simple random samples. Best of luck as you move on.